So in this third lesson, example 1 is dealing with multiple masses. When we draw the free body diagram showing the forces acting on these two masses, that's basically it. Now, there are some other forces that I will talk about in a second, but we don't need to concern ourselves with. This can be labeled as the force due to gravity on the 4.5 kilogram mass, and this can be labeled as the force due to gravity on the 2 kilogram mass. In post-secondary, you also draw in tensions on each mass, but I think from my experience, if we start doing that, it gets too confusing. Let's limit ourselves to these two forces because really those are the real forces acting on them. The basic idea is that the 2 kilogram mass will exert an upward tension on the 4.5 kilogram mass, and the 4.5 kilogram mass is pulling the 2 kilogram mass up. We don't need to worry about that. What we need to recognize is that this pulley results in these two forces being in opposite directions. I really don't think you need to or should draw what I'm about to draw, but in terms of forces on the top of the pulley, there is a force of gravity pulling the pulley that way due to the 4.5 kilogram mass, and there is a force pulling the pulley in the opposite direction due to the weight or force of gravity on the 2 kilogram mass. So the pulley changes those directions. They are still opposing each other. The force of gravity on the 4.5 kilogram mass is trying to rotate the pulley clockwise, but the 2 kilogram mass's weight or force of gravity is trying to rotate it counterclockwise. So when we look at that diagram, and again, I don't really believe that we want to add those forces to the top. You can if you want, but they're not more forces. They're the forces we already have. When you look at that free body diagram, you come to the inescapable conclusion that the net force will have a magnitude that's found by taking the magnitude of the force of gravity on the 4.5 kilogram mass and subtracting the magnitude of the force of gravity on the 2 kilogram mass. It's like Andrea said earlier, and Andrea's left for the day, so she's not here, but she had said earlier that the idea was you take a bigger force minus a smaller force, and the force of gravity on the 4.5 kilograms is bigger. So the bottom line here is we're going to have the following equation, which is interesting. You get Ma equals mg minus mg. But we have to be careful here because these m's are all different. I mean that literally. We have 3 m's in the equation. Each m is different. This m is 4.5 kilograms multiplied by 9.81. The second m is 2 kilograms, and we have to multiply that by 9.81. Now I want you to think about this next question very carefully. What is the mass on the left-hand side of the equation? It is, in fact, Evan, 6.5. Ben, you got it as well. Because when you talk about what's accelerating, what is accelerating is both of the masses are accelerating. So we're going to put the total mass on the other side. This is not really a difficult question, but you need to know how to solve it before you do it on your own. So we're going to calculate the difference between the gravitational forces. 4.5 times 9.81 minus 2 times 9.81. Again, I suppose you could calculate those two forces separately and subtract them, but you get a net force of 24.525. Anybody else up for that force? Okay, so you get 6.5a. Mathematically, you get 6.5a equals 24.525. So you divide both sides by 6.5 to get an answer. So the acceleration of the system is 3.8 meters per second squared. I want to just take a look at the way the question was worded. Yeah, it says, what's the acceleration of the system? So we can't really put a direction on that because different parts of the system accelerate in different directions. If I said to you, what is the acceleration of the 2 kilogram mass, you would say it's 3.8 meters per second squared, up. If I said, what's the acceleration of the 4.5 kilogram mass, I would say it's 3.8 meters per second squared down. Any questions with that example? All right. So now...
oh, sorry. Could you go up a bit? I didn't finish reading some of the stuff down.
Is this what you want to look at, JV?
Just a little higher. Just like the formula for this, because I kind of missed it.
And can you mute your mic, please, JV?
Oh, sure, yeah.
Thanks. So the idea is that you are going to take the larger minus the smaller forces. I would like everybody to take a look at example 2. What you're looking at here is a tabletop. What you're looking at in example 2, give me a second here. JV, have you got everything you need?
Yeah, I'm good.
Okay. Oh, I didn't see you type that. So when we take a look at this, the horizontal piece here is a tabletop. I didn't draw in that. It's not a hovering tabletop. It's not something that's defying the laws of physics, but it's just a tabletop. And on top of the tabletop, we have a 3 kilogram mass. And there's no friction. And the question is, what's the acceleration of the various parts in this? Well, if we draw all of the forces acting on this, there is a force of gravity acting down on the 2.5 kilogram mass. And I'm just going to label that as Fg. And I'm going to hope that everybody understands when you calculate that Fg, you have to use that mass. There is also a force of gravity acting on the 3 kilogram mass, which, by the way, is bigger than the force of gravity acting on the 2.5 kilogram mass. But even though the force due to gravity acting on the 3 kilogram mass is bigger than the force due to gravity acting on the 2 kilogram mass, it doesn't matter because that force of gravity on the 3 kilogram mass is exactly balanced by the normal force between the two objects. So we only have 3 forces acting on the entire system. We have the normal force acting up on the 3 kilogram mass, the force of gravity acting down, and then we also have the force of gravity acting down on the 2.5 kilogram mass. So when we look at this to determine the net force, and the reason why we drew this is so we can determine the net force. The net force will have a magnitude equal to the force of gravity on the 2.5 kilogram mass. Because when I add those 3 forces together, this force and this force cancel. So all I'm left with is the force of gravity on the 2.5 kilogram mass. Okay, so F net equals ma. F net equals ma. But F net is the force of gravity on the 2.5 kilogram mass, which means that the force of gravity on the 2.5 kilogram mass is the net force, which is equal to ma. So this is a weird situation because there's no opposing force. We're not subtracting anything. But what we're going to have is mg equals ma. And you need to recognize that those two masses are different. The mass on the left side is 2.5 kilograms times 9.81 meters per second squared is going to equal the acceleration, the magnitude of the acceleration, times the total mass that accelerates. And when you look up here, we've got 3 kilograms plus 2.5 kilograms, which gives me 5.5 kilograms accelerating. Once again, we are in a realm now where you don't just read a question and look for the formula. That doesn't work anymore. You're not going to find a formula on your formula sheet to solve this problem. You have to build a formula, and the formula we build in this particular case is the mass of the 2.5 times g equals the mass of the system times a. So we have to figure out what this is. I'm going to take 2.5 times 9.81 and divide by 5.5. So do you also get 4.5 meters per second squared? Okay, so the acceleration of the system has a magnitude of 4.5 meters per second squared. If I said, what's the acceleration of the 3 kilogram mass, you would say 4.5 meters per second squared to the right. And if I said, what is the acceleration of the 2.5 kilogram mass, you would say 4.5 meters per second squared towards the floor. So now we add another layer to this. What if there's a coefficient of friction? Now I think you might have to redraw this, but while you're redrawing it, I'm going to start drawing in all of our forces. We have a force of gravity acting on the 2.5 kilogram mass. We have a force of gravity acting down on the 3 kilogram mass. And that's exactly balanced by an equal but opposite normal force upwards. So far this looks like the free body diagram for question 2. This is the force due to gravity on the 2.5 kilogram mass. This is the force due to gravity on the 3 kilogram mass. The force that I've got on the top is the normal force, but now we also have a force of friction. Now, just look up here. If you're doing some calculations, just stop for a second and look up here. What if the force of friction is that long? What would the acceleration be? Well, it would be 0, right? Exactly. It's going to be 0 because there's not enough applied force pulling the thing towards the floor to overcome friction. On the other hand, if the force due to friction is smaller than that force of gravity on the 2.5 kilogram mass, then it will accelerate down. So this is kind of like the situation where we had an incline. Maybe we should calculate the force of friction first before we commit ourselves to a particular drawing. So I go to my formula sheet, force of friction equals mu Fn. I then say to myself that I know on a horizontal surface and this in fact is horizontal, that yellow line is horizontal, I know that on a horizontal surface, the normal force is the force of gravity. There's no component here, it's just the force of gravity, which means the force of friction is mu mg. And we can certainly calculate that. I'm just going to move off to the left-hand side where I got a bit more room. The force of friction will have a magnitude of mu, which is 0.34, times the mass, which is 3 kilograms, times 9.81 meters per second squared. No cosine here because it's on a horizontal surface. I get a force of friction of 10.3 newtons. Well, that means, now we better calculate the force of gravity acting down on the 2.5 kilogram mass as well. So this is the mass, which is 2.5 kilograms, times 9.81. I can see right away the force pulling this down is easily bigger than the opposing force of friction. It's going to be very close to 25 newtons. 2.5 times 9.81 gives 24.525. Oh, right, we had calculated that before. So 24.525 So now we can draw this accurately. Just looking at your screen for a minute, please. If this length is 24.525 newtons and the force of friction is only 10.3, then I need to draw the force of friction a little bit less than half as long. And in fact, that's kind of what I drew here. Okay. So this is the force of friction. So looking at this whole picture now, I'm going to scroll up so that we can see it. Looking at this whole picture at all of the forces, every single force, this force, this force, this force, and this force, the sum of those forces will be F net will be equal to the force of gravity on the 2.5 kilogram mass minus the magnitude of the force of friction. Because the force of friction is opposing that downward force. The pulley is what's making them opposing. So now we can put things in. This is MA equals, we've already calculated these numbers, 24.525 newtons minus the force of friction of 10.3. I think it was 005 newtons. The mass here is the total mass of 5.5 kilograms, which means the acceleration is found by subtracting those two forces and dividing by that mass. So the acceleration will be equal to 24.525 newtons minus 10.3005 newtons over 5.5 kilograms. Anybody else get 2.6? So 2.58, we would round to 2.6 based on the numbers in the question. So the answer to this question is 2.6 meters per second squared. Regardless of direction, the magnitude is 2.6 meters per second squared. The mass on the tabletop would be 2.6 meters per second squared to the right. The 2.5 kilogram mass would be 2.6 meters per second squared down, and the pulley would be 2.6 meters per second squared clockwise. And that's it. Now, admittedly, there is a question here in your assignment that is more complicated. All of a sudden, I've got 3 objects. But just to so did I use the wrong number for the coefficient of friction? Thank you. For some reason, when I did my calculation, I used 0.35 instead of 0.34. So if you use 0.34, your numbers are going to be a little bit different. But okay, I understand what I did there. But you get the idea, I hope. If we take a look at the first question in the assignment, if this thing rotates, common sense says it will rotate in this direction because the 8 kilogram pail is more massive than the 6 kilogram pail. Well, what you're talking about doing here then is saying that you have an applied force down, an applied force down. You also have a force here that's balanced by a force there, so that's really not relevant. In the first question, if it's frictionless, you can take the mass times 9.81 of the 8 kilogram minus the mass times the 9.81 of the 6 kilogram. But you're going to have to use the total mass. In the next question, in question 3 I want to go to, no, let's go to, no, I guess that's it. Do any of these have friction? I guess not. You don't even have to calculate forces of friction for these, which is unfortunate. I'm going to come up with some that we'll work on at some later point in time where there's friction. But anyway, that's your assignment. You've got 3 problems, I think, to work on here. Finish up that last problem in the last section, and you have about 15 minutes before 11 o'clock, which is when the class officially ends. But as always, I'll be here till 11:30.